Hi, this is Dr. Jack Jackson. I'm going to be talking today about the standards for mathematical practice. These standards for mathematical practice are the heart and soul of the Common Core standards for mathematics. These Common Core state standards are national standards that have been put together for K-12 mathematics that have since been adopted by most of the states, including Arkansas and Oklahoma. They describe a mathematically proficient learner. They're basically 8 statements or standards followed by a narrative which has been rewritten as a bulleted list that's going to elaborate the standards. So I've taken the narrative below each of these standards that are in the document and rewritten them in a little bit easier way to follow for this PowerPoint. These describe the primary goals of K-12 mathematics instruction. These, again, are the heart and soul of these standards. The standards will say we teach a certain topic in certain grade levels, but these standards are process standards, and these are the standards for how we practice mathematics, what we expect our students to really know and be able to do. Not specific skills, but more general ideas. And these are really what we're after. As you read through these, you'll notice that there's an increased expectation of the depth of knowledge and skill expected of students at all levels. We're expecting much more in the way of making connections and being able to explain and do and really understand at a deeper level. And the primary goal of all university mathematics instruction is really to develop these same skills. So specific skills taught in mathematics classes are important, but they are secondary to developing these general mathematical reasoning skills, which are applicable for everyone in their daily lives. So really the main goal of all of my mathematics classes that I teach is to develop skills with these 8 standards. So let's take a look at the standards. Here are the basic 8 standards. Make sense of problems and persevere in solving them. Reason abstractly and quantitatively. Construct viable arguments and critique the reasoning of others. Model with mathematics. Use appropriate tools strategically. Attend to precision. Look for and make use of structure. Look for and express regularity in repeated reasoning. Now let's examine each one of these statements and see if we can understand a little bit more about what this means. Number 1, make sense of problems and persevere in solving them. So we want to find meaning in a problem. Finding an entry point for a solution. So if we're trying to problem solve, we want to be able to find where to start. We want to analyze the given information, the constraints, the relationships, and the goals of problems. We want to make conjectures about solutions. Conjectures are possible ideas that we think might be true, but we still have to test them out. We might want to consider analogous problems. So go into other problems, both as a solution to solving the problem that we have, and also as a way to extend. We might want to examine special cases of a problem before we move on to the general solution. We want to be able to monitor and evaluate our progress as we go along so that we can see each step of the way. Is this making sense? Are we making progress toward our goal? We want to be able to explain relationships that we see inherent in the situation that's there and see how these might relate to our problem-solving efforts. We want to use tools such as graphs, equations, concrete models, tables, and words. Sometimes this is referred to as the rule of 5, that every concept that we try to do, we're going to try to represent these 5 ways, with graphs and pictures, equations and algebra and formulas, concrete models, actual physical representations, tables and numbers, and then finally describe it verbally with words. So we want to use these 5 ways of representing mathematics and use all of these to help us understand and solve problems. We want to check solutions using sense-making and alternative strategies. See if there's another way to solve the problem. Check our answer and to see if it makes sense. And of course, this idea of perseverance is also extremely important. One of the things that we learn about in mathematics is to be able to persevere. Not every problem can be worked in just a few seconds or a few minutes. The more challenging the problems get, as the mathematics courses get more and more advanced, particularly as they get into college level mathematics and more upper level college mathematics, the problems become more and more complicated, and it takes more and more perseverance to be able to come up with solutions. The second standard is reason abstractly and quantitatively. So by that we mean we want to make sense of quantities and their relationships. We want to go back and forth between contextualizing and decontextualizing. Mathematics is very applicable to many real-world situations. So we want to take an idea that we have that may be an abstract idea, and then we want to make it concrete. We want to contextualize it within some specific real-world context. But we also want to be able to go the other direction. We want to take something that is contextualized in a particular context, and we want to decontextualize that. We want to be able to pull some general mathematical concepts from that so that we can then turn and contextualize it again in a different context. So we want to go from a concrete situation to an abstract principle, and then go back from that abstract principle and apply it maybe in the same or different concrete context. Similarly, we want to go from specific examples to the general problem, or from the general solution to specific examples. So we may want to be able to describe in detail some specific relationships and then extrapolate from them some sort of general relationships. But then we also sometimes want to go the other way, where we're given a general relationship and say, oh, these examples are specific examples that. Related to this is going from local to global. We may want to look at something that applies in a very specific local situation and then go out and see what applies in the overall global situation, or vice versa. We want to be able to use appropriate symbolic notation. So mathematics has its own jargon and its own symbols, and just as any field of knowledge or field of study, we're going to have certain things that are specific to the discipline, where we have to learn the symbols, the notation, and the terms. And so we want to be able to use those appropriately. And honestly, most of those symbols that we use are really just ways of being able to precisely and simply say something, some mathematical concept. And so we use these to simplify things. But part of learning mathematics is learning that. We want to be able to reason both quantitatively and qualitatively. Both quantitatively means numbers, be able to describe things with numbers and quantify things. For example, one of the big ideas about statistics class, for example, is taking something that's uncertain and putting a number to it to quantify that. That's assigning a probability. Or, for example, we may want to use data to help us make decisions. Also, though, we want to be able to describe things qualitatively, to describe their properties and things that we see there that are maybe not necessarily numerical in a sense as well. So mathematics is not just about numbers. It certainly includes that, but that's not all. We want to be able to make sense of units. Anytime you have almost any time you have a real-world situation, there are going to be some sort of units, whether that's feet or inches or centimeters or pounds or whatever, and we want to be able to take those units, understand what the units mean, and make sure that we are using appropriate units and understand what those units mean. And understand the meaning of quantities. So whenever we're working with mathematics, we want to make sure that any quantities that we see, we have a meaning of understand the meaning of what that means, both in sort of an abstract number sense, for example, or perhaps in the context of the problem or the real-world application that we're doing. What do those quantities mean? And so we want to find and make use of properties of numbers and other kinds of mathematical objects and see what kind of properties they have and use those properties to help us reason mathematically. So we want to be able to reason on an abstract level and a more concrete level as well. Construct viable arguments and critique the reasoning of others. As a mathematician, I would say this is really probably the heart and soul of mathematics, is understanding logic and reasoning. Constructing and evaluating logically valid mathematical proofs is really the heart and soul of what mathematics is all about. It's being able to explain your reasoning and justify it. And of course, to do that, we're going to use and understand stated assumptions, definitions, previously established results, and rules of logic to help us write out these reasoning proofs, the proofs that show and describe what our reasoning is. And often this follows a pattern where we do some sort of exploration. In fact, mathematics, when it's done in its best way, what you do is you start by exploring something, and then you make a conjecture, and a conjecture is an educated guess at what you think you know what's happening. But then you test that out, and you maybe find an example where it doesn't work and you've chosen your conjecture is false. That's called a counterexample. So we want to be able to recognize and find those counterexamples. But we also want to be able to maybe find examples. If we think it does work, we find those. If we can't find any counterexamples, we found a lot of examples that are there. That gives us some idea that this might be true. Then we want to go in and see if we can make a proof out of that. So we explore, then make the conjecture, test the conjecture, then find a reason why it's true, and make the argument and write the proof. When we're dealing with an argument, we might want to break it down into cases and look at those cases. We want to be able to justify conclusions and the intermediate steps of our argument along the way. So it's not enough just to have steps to a process. We need to be able to explain why those steps are used and why they work. We want to be able to place our arguments into the appropriate context. So make sure that we understand how our arguments fit within the context of the problem and make arguments appropriate to that context. Compare and evaluate multiple plausible arguments. Maybe there's not just one way to argue or to justify what we've got, our conclusions. We want to be able to look for multiple ways of doing things and to validate that. We want to be able to identify correct and flawed logic of our own and others. So when we look at a logic, an argument, we will be able to tell, is it really logical or not? This is important in lots of areas of everyday life, not only just in a mathematics classroom, but also in evaluating logic that maybe someone is trying to convince you to do something, whether that's a salesman or a politician or whatever. You need to be able to understand their logic and to see if it's correct or not. And if it's flawed, what's wrong with it. We want to use multiple representations with concrete and abstract elements to build and communicate our valid arguments. So we want to illustrate our reasoning as well as we can with specific concrete examples and then more general abstract elements as well. And we need to identify what are the required assumptions for these valid arguments. So what was it that made our argument work and to reach our conclusion? So we know we have to have those assumptions before we can reach the conclusion. If you change the assumptions, perhaps the conclusion is different. So we need to be able to construct arguments that are logical and critique the reasoning of others. Model with mathematics. We want to apply mathematics to solve problems in everyday life, society, and the workplace. we want to connect mathematical concepts to practical applications. So notice that this is one area of mathematics that's very practical. The constructing arguments may be considered somewhat more, a little bit more abstract. This is a very practical area when we're dealing with modeling. We want to identify relationships between input and output quantities, cause and effect. When you do something, what are going to be the consequences of that action? Okay, that's part of what mathematics is about, and understanding cause and effect in mathematics can help you in many areas of life. We want to make appropriate assumptions and approximations to simplify a solution. Okay, so sometimes we get a situation that's too complex, and so we will model that with a simpler model. Perhaps maybe we have some data points that are not really in a straight line, but they're close enough to a straight line. We can simplify that to a straight line model that we can use effectively to model the situation. We want to be able to revise solutions and strategies based on new information and changing circumstances. So we need to be adaptable. Okay? If the situation changes, we get new information, we have to be able to revise our strategy to obtain a solution in the new situation. Identify, illustrate, and communicate important relationships among quantities using all kinds of things such as diagrams, graphs, tables, flowcharts, formulas. So both visual elements and numerical elements, we want to put all these together to help us communicate these relationships. We want to analyze relationships mathematically to draw valid conclusions. This is one of the big things that we want to be able to understand in applying mathematics to the real world, is that when we make decisions, decisions should be based on data as much as possible, and try to rely as little as possible on just a gut feeling or some anecdotal information. Try to actually collect some data and analyze the relationships that we see mathematically to get some actual numbers, qualitative and quantitative measurements if we can, to help us draw valid conclusions based on data. Interpret mathematical results in the context of a situation. So part of when we're talking about modeling is taking mathematics and putting it in a real-world situation. What does it mean in that context? Standard number 5 is to use appropriate tools strategically. So we want to consider multiple tools and choose the appropriate tools for the task at hand. Understand the advantages and limitations of each tool. So how do we use tools? Well, we want to use them to build knowledge and to deepen understanding, to visualize, to compute, to estimate, to verify, to predict, and to explore consequences. Now, depending on the task at hand, we might use a whole host of different tools. So here are some examples. Certainly, just use our minds to think, and then we have tools such as just a simple pencil and paper tools for recording our thoughts. We might use concrete models and manipulatives to illustrate or to help us discover certain mathematical concepts and relationships. Probably in your schoolwork you use some kind of standard manipulatives somewhere along the line to help you understand some basic concepts about number. We want to use drawing and measuring tools, things like a compass, a straight edge, a ruler, yardstick, measuring things, measuring cups, etc. We want to be able to use calculators, appropriately use these things. Computer software, including dynamic geometry software, statistical packages, computer algebra systems, spreadsheets, and web resources. So all of these things, we need to choose the appropriate tool at hand, and we need to be comfortable using tools at different levels. So in mathematics classes, sometimes you'll be asked to do something, maybe it's only pencil and paper. You're expected to be able to do it without the use of a calculator. Other times we're going to use a calculator or computer software very much to help us in our not only in our application and to make computations easier, but also to do some of these other things up here, to visualize, to compute, to estimate, to verify, predict, explore consequences. The whole point of using these tools is to help us build our knowledge and deepen our understanding. And yes, it does make computations easier in some cases, such as a calculator, but the point of the calculator really is to help us understand the mathematics better. Standard 6 is attention to precision. We want to be able to communicate precisely to the others. We want to make explicit use of clear definitions. So, we have to be very clear about what our definitions are of our terms and use those definitions very carefully. We want to be able to state the meaning of symbols using them appropriately and consistently. So if we introduce a variable, for example, in a problem, we need to say, what does that variable represent? We want to be very clear about that. We want to be very precise. If we say two things are equal, they need to actually be equal. We need to actually make statements. We need verbs on the paper, whether that's in the form of an equal sign or a less than sign, or whether that's actual English words or whatever language you're working in. But we need to actually make statements, and those statements we need to be precise and true. We need to be sure we pay attention to our units of measure and specify them. If we have a problem, there's a big difference in a length being 3 centimeters and 3 miles. It makes a difference. We need to make sure that we say their appropriate unit and include that. That's an important part of the problem. We want to carefully label anything that we have. For example, we want to carefully label the axes, the numbers on the axes, the scales, and any kind of graphs that we have, and make sure that we label titles and so forth on our graphs so that we're very precise about that. And we want to calculate accurately and efficiently. We want to be able to express numerical answers with appropriate precision. We want to round off to the appropriate place in our final answers, but never round off in the middle of a calculation. We want to be sure that we are very precise about what we do. And attention to precision is a very important standard for mathematical practice. And again, like all of the other practices, this is something that can help you in many, many areas of your life. Standard 7 is look for and make use of structure. So we want to discover and describe patterns and structure that we see. And then we want to generalize and extend those patterns and structure. We want to utilize strategies for drawing or computing additional information to discover structure. So we don't see the structure yet. What do we do? What can we compute or find or explore to help us find the structure? So we want to look at subparts of, say, geometric objects or algebraic expressions and determine their meaning. We have a fraction. What does the numerator represent? What does the denominator represent? Or we have a formula, changing one parameter in the formula, or changing a coefficient here, or a number there, or an exponent there, here or there, or something. Changing something in that formula. How does that change the graph and the table? And what kind of structure do we see in the formula, in the table, in the graph of a function, for example? And we want to be able to classify mathematical objects. Like this might be some geometric figures, or it might be other types of objects, but we want to classify them according to similar characteristics, and maybe describe the general characteristics for that whole class of objects, which then applies to every example within that, or every subclass. So this idea of discovery is very, very important. So part of mathematics is discovering new ideas, to look for patterns, find those patterns, describe them, and then maybe go then and tie this together with one of the other standards, prove that these patterns are going to continue. The 8 standards look for and express regularity in repeated reasoning. Repeated calculations will often lead to general methods and shortcuts. So as we're working through a problem, we may do 4 or 5 examples, and they're all very similar. And then we may say, okay, well, from those we can glean some general method that will allow us to work in general. If we can prove that that method is in fact general and works all the time, then we can use that perhaps as a shortcut to work that sort of a problem. Repeated steps often allow us to go to abstraction. So if we repeat a certain number of steps over and over again and we're doing the same thing, we may find that, oh, that leads us to a more general method or an abstract way of even looking at it, which even helps us to do things such as deriving formulas. So we may be able to derive some general formulas. One example from algebra class is if you complete the square several times, you will realize that this is, we're repeating the same steps over and over again. We should be able to abstract this somehow. So we put in letters in place of the numbers and come up with an abstract formula, which is the quadratic formula, for example. And so we can derive a formula that way. Evaluate the reasonableness of intermediate and final results. Okay, we want to be able to see if our results along the way and then our final result makes sense. And we want to maintain oversight of problem solving while attending to the details. So, again, those are the 8 standards. Make sense of problems and persevere in solving them. Reason abstractly and quantitatively. Construct viable arguments and critique the reasoning of others. Model with the mathematics. Use appropriate tools strategically. Attend to precision. Look for and make use of structure. Look for and express regularity in repeated reasoning. And these things are not isolated. These 8 standards are interconnected. So we may, in a particular task that we might be doing, it may involve possibly all 8 of these standards or some combination of them. And my final slide puts all of this together, and you can see this. And this is actually printed out in a huge poster that's in the hallway in math science on the 2nd floor at the University of Arkansas Fort Smith. I've posted it there, and you can see it posted there. So again, these standards for mathematical practice describe what a mathematically proficient learner at all grade levels, K through 12, but not only there, also in college as well. And so my goal, my main overriding goal, is to develop mathematical reasoning, these general kinds of skills in students. The specific skills that are specific to each class are very important. In most cases, they're very applicable to the real world, but that's not nearly as important as these general skills, these general thinking abilities. Because these skills, these 8 standards that we're going to develop in students, these will stay with you no matter what you do in life.